Here I welcome Dr. Abila Jabaquin, Assistant Professor of Physics, to welcome and introduce today's resource person to the attendees.
Good morning, everyone. I'm happy to welcome each and everyone for the second day of 2 days international conference on advances in physics organized by the Department of Physics, Holy Cross College, Autonomous, Nagarkoil. I deem it a great privilege to introduce our guest of honor and speaker, Dr. R. Justin Josephus, Associate Professor, Department of Physics, NIT, Tiruchirappalli, who is going to enrich our knowledge on iron 57 Mossbauer spectrometry. Now, I would like to place a record of few words about his academic achievements. He was awarded PhD by the University of Madras in the year 2005. His research title is Size-Dependent Magnetic Properties of Nanocrystalline Manganese Zinc Ferrite Garnets and Permanent Magnetic Materials. He also completed postdoctoral research in Graduate School of Environmental Studies, Tohoku University, Japan. His current area of interest is to obtain enhanced magnetic properties in nanoparticles. He received fellowship from UGC, CSIR SRF, MEXT Research Fellow, and COE Fellow from Japan. He has published more than 40 research articles in international journals with totally 1,780 citations, 20 H index, and 30 I-10 index. So far, he had completed 2 projects under DST. He presented 37 papers in conferences and edited 2 books. He also the recipient of Best Poster Presentation Award and Chartered Physicist Award. He was the faculty advisor for Nakshatra Science and Astronomy Club, Fixion Club, and have membership in Indian Physics Association, Magnetic Society of India, Materials Research Society of India, Indian Society for Non-Destructive Testing, and elected member in Institute of Physics UK. We are indeed honored for this opportunity to listen such an eminent professor. On behalf of the Department of Physics, Holy Cross College, Nagarkoil, I extend you a warm welcome, sir. Now, I request Dr. R. Justin Josephus to enlighten on the topic Iron 57 Mossbauer spectrometry. Over to you, sir.
Thank you. I'm going to share my screen. Just inform me if it is full screen or not. Okay. Can you see my screen?
Yes, sir.
Okay. So good morning to all of you. I'm indeed thankful to all of you for attending this lecture. So I will be talking about iron 57 Mossbauer spectroscopy. It is also known as spectrometry when you deal with applications. And I am from NIT, Tiruchirappalli, and from the Department of Physics and from the Magnetic Materials group. Let me go to the contents. I will be dealing with the fundamentals of Mossbauer effect, then 1 or 2 slides on instrumentation, then about Mossbauer parameters, that is what we can do with Mossbauer effect, and then finally on applications. And probably you may have Mossbauer effect in your postgraduate studies. And if you are not having it, probably you may learn it later on. And if any one of you are going towards research, then you can, from this lecture, you can understand in what way Mossbauer effect is useful for your research characterization. That is the objective of the presentation. Okay. So we will start with the phenomena of Mossbauer effect. That is, what is Mossbauer effect? Then about instrumentation and the parameters. Three major parameters are there: Isoshift, quadruple splitting, and hyperfine splitting. And if you are understanding this, it may also help you to understand these parameters in NMR, nuclear magnetic resonance. Maybe yesterday you may have learned about fundamentals of magnetism by Dr. Ponpandian. He may have already mentioned you about hysteresis loop. Hysteresis loop is a bulk characterization technique. That is, now you are going to obtain the magnetic properties of whole sample. The whole sample. Okay, so the whole sample you are measuring using vibrating sample magnetometer. So that is the equipment used to measure hysteresis loop. And you may have seen that in the x-axis you have applied field, and in the y-axis you have magnetization in the hysteresis loop. So the applied field is obtained using an electromagnet, which is shown here. So we have electromagnet. Then that will produce applied magnetic field. In the presence of applied magnetic field, what is the magnetization? That is measured using the vibrating sample magnetometer. Today we are going to deal with local magnetic measurements. Local means you can go to the atomic level, one atom, or you can go to a crystal. So a crystal is made up of atoms in the corners or center position or face centered position. So you will measure the magnetic properties of the atoms or crystals, and we can characterize the bulk material using the Mossbauer effect. So from the atomic level you can go to the large bulk level. Okay. So what is Mossbauer effect? Please understand. If you want to remember, you can remember in one line itself. Mossbauer effect is recoil-free emission and resonant absorption of nuclear gamma rays in solids. I'll tell you about what is recoil-free emission and what is resonant absorption and what is nuclear gamma rays. But understand that it is a resonant absorption and it is free from recoil, and it involves gamma ray. And this is how it looks like. In the previous slide you have seen how the hysteresis loop look like. Similarly, what will be the spectrum of Mossbauer effect? It can be a singlet, a doublet, 2-line spectrum, or a sextet, a 6-line spectrum, or a combination of all. It can be a combination of 2 sextet, 3 sextet. It can be a combination of a single sextet and a doublet. But we have to interpret it. If you want to interpret it, we need to understand fundamentals about it. There are hardly few people in this national level or even the global level who are undertaking research in Mossbauer effect, because there are certain difficulties associated with it. But understanding the concept may be quite easy for a physicist. Okay. It was discovered in 1957 by Mossbauer in Germany, And Mossbauer received the Nobel Prize. He is one of the youngest person who received the Nobel Prize. Okay. In the x-axis, you have velocity, relative velocity, and the y-axis you have transmission intensity. So that will be the typical Mossbauer spectrum. So now going to the next slide. If you see the fundamentals, you have seen like what is Mossbauer effect, recoil-free emission, and resonant absorption of nuclear gamma rays in solids. So we have nuclear gamma rays. So how can you get gamma ray? So if you have an excited state, okay, so let's say you have an excited state and you have a ground state, then what will happen? When there is a transition from the excited state to the ground state, there will be an emission of gamma ray photon. If it is high energy, it is gamma ray. Okay. If it is low energy, as in visible light, it can be a visible light photon. So the primary idea is the excited state. From the excited state, when the nucleus comes to the ground state, there will be emission of the energy in the form of gamma ray. So gamma ray is emitted, and the energy of the gamma ray is 14.4 keV in the case of iron 57 Mossbauer spectrometry. So the title is specifically given as iron 57 Mossbauer spectroscopy because spectrometry, because there can be different types of nucleus which can be used to study the properties of materials. And if you are taking a material for study, we have to use the same nucleus. So let us say if you are having a material such as Al2O3, you cannot use Fe57 Mossbauer spectroscopy. You cannot use, because the nucleus in Fe57 Mossbauer spectroscopy is iron, but your material does not have iron in it. So understand the difference. Why iron 57 Mossbauer spectroscopy is like if you are using iron 57 Mossbauer spectroscopy, we can study only iron-based compounds. So that is the reason. The type of nucleus is very important. Okay. So when it comes to the ground state, it emits a photon, and the photon which is emitted can be used to study the properties of materials. How? Okay. So we also had another sentence. Okay. Nuclear recoil-free emission and resonant absorption of nuclear gamma rays in solids. I told you what is nuclear gamma rays, and we also have resonant absorption, and then later on we also have recoil-free emission. So what is resonant absorption? What is resonance? So I told you a gamma ray will be emitted when the nucleus comes to the ground state from the excited state, right? So the emitted gamma ray will be absorbed. Okay, so this is emission, because the gamma ray is emitted, and the emitted gamma ray will be absorbed by a nucleus in the ground state. So from the ground state, another nucleus will absorb the gamma ray, and it will go to the excited state. The main thing lies here is when condition for absorption. What is the condition for absorption? Only when the gamma ray energy is equal to the difference in the energy level between the excited state and the ground state. Okay. When the difference in the energy level between the excited state and the ground state of the absorbing nucleus is equal to the incoming gamma ray energy of the photon, then only you will have absorption. Very, very important condition. Okay. So in reality, what happens is like, no, when the gamma ray is emitted, what happens is, no, there will be recoil. Okay. So that is one of the physical phenomena, right? Physics will not be violated anywhere, even at the nuclear level. So if you want to understand what is recoil, you can easily imagine a gunshot. Okay. Bullet goes forward, the gun goes backward. So similarly, when the gamma ray comes forward, the whole nucleus, because the gamma ray is coming from the nucleus, so the whole nucleus will go backward. So there will be an energy loss. Okay. So in reality, you will see a energy gap is widened like this. Okay. So in reality, you are not having a E gamma readily available, which is equivalent to 14.4 keV for absorption. Due to the recoil, your energy is increased. So, in order to have resonant absorption, we have to match the energy which is equal to the gamma ray energy plus recoil energy. So when you match this energy, then only absorption can happen. Okay. So that is the main concept behind Mossbauer effect. So imagine that the whole lattice is at rest before gamma ray emission, and after gamma ray emission there is recoil. Then the recoil energy ER can be easily obtained from E gamma square by 2 into Mn lattice mass T square. Okay. So what Mossbauer did is this. So the center ball is the nucleus which is emitting gamma ray. So when the nucleus is emitting gamma ray freely, what happens? This energy, as we know, the mass into velocity, momentum is equal to mass into velocity. So let us say, if your mass is small, then more will be the backward motion. So if you have a free nucleus, more will be the backward motion, so more will be the recoil loss. So we have to arrest the recoil. So in order to arrest the recoil, the nucleus has to be embedded in a lattice. So when you embed this in the lattice, the whole lattice mass has to be considered now. So instead of a single atomic mass, now the mass of the whole lattice, Mn, will be very, very large. So the recoil energy ER is inversely proportional to the mass of the lattice. So since the mass of the lattice is the order of 6.023 into 10 power 23 Avogadro number, so that is very, very large. Since that is in the denominator, now your recoil energy loss will be very, very less. Okay. And another way to minimize the recoil energy loss is to reduce the gamma ray energy. But gamma ray energy for iron 57 is fixed, that is 14.4 keV. So we have to use the lowest energy, that is 14.4 keV. So if there are other energies available, then we should not use that. Okay, so minimum energy of the gamma ray and maximum mass of the lattice has to be used in order to reduce the recoil. So just recollect the definition of Mossbauer effect: recoil-free emission. Then when the gamma ray is coming without recoil, then it has to be resonantly absorbed by the absorbing nucleus. Then that will give rise to your Mossbauer spectrometry. Okay. I hope you have understood this part very clearly. And suppose now if your sample is having a higher energy, sample is having a higher energy, and if your gamma ray is coming out coming out from the nucleus, then you will not have sufficient energy for the absorption process to take place because it is not now in resonance. So if you want to have a resonant effect, then incoming gamma rays energy should match with your sample. But in reality, what will happen? All your samples, they may not have the same energy level. You have different types of samples. You have iron, you have iron oxide, you have Fe3O4 magnetite, you have Fe2O3, okay, hematite, lot of samples. Okay? In each sample, the iron is in different chemical environment. So what will happen? Your nuclear energy in the sample is not always equal to the incoming gamma ray energy. Okay, the incoming gamma ray energy is coming from a source. I hope you understand the difference between sample and source. Source is the place where the gamma ray originates. Okay, and sample is your sample. Okay, so we have to match the energy of the incoming gamma ray with your sample, then only there will be a resonant effect. How to match it? Using Doppler effect. What is Doppler effect? If you take a vehicle that is an ambulance which is approaching us, then the frequency will increase, and if it is moving away from us, the frequency will decrease. So that is Doppler effect, which we learned in the lower classes. Same effect is used here. So if you want to increase the energy, you have to give a Doppler effect that is approaching the sample. So your source should move, the whole source should move towards the sample. So when it moves towards the sample, then you can increase the energy, and then you can match the energy of your sample. And if your energy is less, your sample energy is less, then you have to move the source away with the velocity, with the negative velocity we have to give. So then your energy will be less. So that approach is used in Mossbauer effect. So recoil-free emission happens in the case of source. How we do that? We put the nucleus in a lattice that will be having a larger mass. So recoil-free emission will happen in the source, and then in your sample we have resonant absorption by matching the energy of the incoming gamma ray by giving a Doppler shift. That's all. That's all about Mossbauer effect. Okay. So then what will be the instrumentation? Instrumentation, we have a transducer, we have absorber. Absorber is nothing but a sample. Okay. Then we have the source. Okay. Why we need a transducer? In order to give backward and forward motion. Why we need backward and forward motion? We have to match the energy of the sample with the incoming gamma ray energy. Okay. Then after the sample absorbs the gamma ray, we will use a detector to detect what is the energy level present in the sample. That's all. Okay. So that is these three are the main parts of a Mossbauer spectrometer, and all the associated electronics are related to it. Driving unit to give the backward forward motion, and the function generator to give the electrical signal for the forward backward motion. Then we have the data acquisition system with the multi-channel analyzer. Then it goes to the PC, and we need an analysis PC. In the detector part, we have high power supply, extra high tension high power supply. Then we also have a pre-amplifier for impedance matching and signal amplification. Then we will have a linear amplifier, okay, which amplifies the incoming signal. And then we have the analog to digital converter, and this analog to digital converter, the output is fed to the multi-channel analyzer data acquisition system. So this is the block diagram of the Mossbauer spectrometer. Okay. So this is how the instrument looks like, Mossbauer, but it is very difficult for you to identify the parts in this chunk-like arrangement, but you can see the right side. Right side image, we have the absorber here at the center. Then we have the drive unit. So drive unit is to produce forward-backward motion. So that is similar to a loudspeaker. So loudspeaker, you give electrical signal. So the electrical signal will be converted to mechanical energy. So mechanical energy, if you give a regular signal, if you are speaking, no, the electrical signal will not be a regular signal. If you give a regular sine wave, then that is a regular signal that can translate to forward-backward motion. So your drive can move forward-backward, and it can give some energy, and whichever energy matches with your sample energy will be absorbed, and the leftover thing can be noted by the detector, and this detector can tell you what is your sample energy. That is how. So that is how the system Mossbauer spectrometer works. Okay. And we also can do measurements at room temperature, very low temperature, and even high temperature. So for which the system becomes somewhat complicated. That's all. Okay. What are the elements that can be studied with Mossbauer spectroscopy? Not all the elements. We have most studied iron. Okay. Why we cannot study all the elements? We need the condition that no recoil energy should be minimum. Recoil energy can be minimum only if your E gamma, incoming gamma, is less. If your incoming gamma is very large, you cannot do that. So certain nuclei only satisfy this condition. Then since this use gamma rays nuclei, you know that it is subjected to the radioactive decay loss, and that means it will have a definite lifetime. So if you are using a particular nuclei, then we should have sufficient time for studying. Suppose now if your lifetime is like only 1 hour, by the time you transport it from somewhere and take it to the laboratory, your gamma ray will be gone off. So iron, it has very good conditions satisfying that it is 14.4 keV the energy. It has a lifetime of nearly a year. So all these conditions make us to study iron-based materials. It is also fortunate that iron is responsible for the strongly ferromagnetic behavior. Okay. So we see here, it is 270 days for iron, 14.4 keV. Then the spectrum will be having a half width of 0.19 millimeter per second. We are translating the energy in the form of velocity. Okay. In the y-axis, we have velocity. That is nothing but when you are making a forward motion, your velocity will be positive and it will be having a higher frequency. Okay. And if it is moving backward, if your drive is moving backward, or if your source is moving backward, we will having a negative velocity. So in the spectrum, you will have positive and negative velocity. So then about parameters, Mossbauer parameters, we have isomer shift. Simply you just remember it is a measure of the size of the nucleus. The nucleus can be either large or nuclear radius can increase or decrease, okay, in the excited state compared to the ground state. So that difference will be measured. So that is isomer shift. The charge density will be varying in the excited state and the ground state. So that will be measured. So that gives you isomer shift. When can this vary? According to your environment, chemical environment. So chemical environment can be studied using Mossbauer effect. How? Using the isomer shift. So isomer shift can give you a measure of bonding, charge state, d electrons. Okay. Because now isomer shift is a measure of electron density, s electron density. Okay. S electron density depends on d shielding. Okay. If it is more shielded, then d electron density cannot reach the s, cannot contribute to the s shell. So that will also give rise to the difference in the isomer shift. Okay. So from the isomer shift values, we can find the charge state, whether it is ion is +2 oxidation state, +3 oxidation state, high spin state, low spin state, etc. From the measure of the isomer shift. Okay, that is given here, positive or negative. So most of them will be positive. So that is now high energy state like that. So we can measure the isomer shift and subsequently the charge state. Also the spin state. Okay, high spin or low spin state. The next parameter is the quadrupole splitting. Quadrupole splitting is the measure of, earlier we have seen about the size. Okay, isomer shift is a measure of size, bigger or smaller size. Quadrupole splitting is a measure of shape, whether it is spherical shape or non-spherical shape. Spherical shape means ground state. Non-spherical shape means excited state. How can it go to the excited state? If you are having atoms, we have electrons, so the electrons will induce electric field on the nucleus. So as a result, let's say like now we are not having few atoms at the corner here. Okay, then what will happen? There will be electric field on the other side, which will make the nuclear charge distribution to elongate. Then we will get a quadrupole splitting. Okay, so that is quadrupole splitting. Then that will give rise to a spectrum like this, a double line spectrum. So the distance between the two lines, two Lorentzian, inverted Lorentzian lines, will give you the measure of the quadrupole splitting. If this distance between the two lines is very large, we can say we have a very, very asymmetric nucleus. That means no, you are having a very defective sample. Okay. So that is the interpretation which you can make from the quadrupole splitting. The next one is the hyperfine splitting. Hyperfine splitting will give you the magnetic moment or internal magnetic field. Internal magnetic field can be obtained from the hyperfine field measurements. So you have a structure like this, 6-line pattern like this. If you have a 6-line pattern, we can say your sample is magnetic. Magnetic means it can be ferromagnetic or antiferromagnetic. Okay, got it? So from the Mossbauer parameters, we can say whether your material is ferromagnetic, antiferromagnetic, paramagnetic, whether your structure is distorted, whether you are having more defects in your sample. Then we can also find the charge state from the isomer shift. Got it? Okay. And if you see here this spectrum, it is not symmetric. It is shifted towards the right. So that means no, you are having an isomer shift. Okay. If you are not having isomer shift, it will be centered at 0. Correct? So that is how we can interpret the Mossbauer spectrum. Okay. With this, we will go on to the applications. Okay. So we have seen the Mossbauer spectrometer. So Mossbauer spectrometer has been sent to Moss, okay, to monitor the elements present in the Moss. Of course, now we have elements there, iron-based elements there, and the Mars exploration rover, it has spirit and opportunity. So those two rovers were sent for analysis to Mars, and you can see the Mossbauer spectrometer in the rover. Okay, and Mars exploration rover Spirit, it has pictured this plane of Mars and a hill. Okay, so this plane is the crater, Gusow crater. Okay, and this hill is the Columbia Hill. which was pictured by the Mars Exploration Rover. Then on the way from Gusev crater to these hills, different hills, the mineralogy was recorded. And if you see here, the Gusev plain, this is the landing site. The Mossbauer spectrometer recorded olivine and pyroxene. This is iron-based minerals with the silicon. Okay. So these were recorded in the landing site, and as it approaches the hill, okay, the Mossbauer spectrometer recorded hematite and goethite. These are antiferromagnetic iron oxides, and as it moved towards the top of the hill, the spectrometer recorded ilmenite and iron sulfide. Okay. And in this way, this is the first exploration rover which was sent beyond Earth. The moon soil, no, it was easy because now we can return back the moon soil and we can analyze using the Mossbauer spectrometer. That has been done. But for the Mars, no, returning is a very costly affair. So they send the Mossbauer spectrometer along with the rover. And surprisingly, the Mossbauer spectrometer was used to study the Mars, and it gave the information that no, previously Mars was flooded with water. Okay, so there was water long back in Mars. So you can see small spherules like this. Those were shaped using the flow of water, and this has been recorded by the Mossbauer spectrometer. And it has the soil in the Mars has undergone extensive weathering, oxidative weathering. So when there is water flow, then what happens? You can see like no iron, neutral iron. If you are putting it in iron water, what will happen? It will corrode, and it will turn to Fe2 plus, and then to Fe3 plus. So the corrosion product is high oxidative ferric ion. That is what happens here in the Mars also. So you have ferric ion. That is an oxidation product of iron due to the flow of water. Okay. So this spectrum has recorded, the spectrometer recorded that, and the red color of the Mars is due to the ferric content. Okay, the ferric content in there. So even you have nano. So you have a layer of nanoferric oxide on the surface of the Mars, which has been proved by the Mossbauer spectrometer experiments, and that's why you get the red color of Mars. Okay. So the gun coming to the ground, okay, that is Earth, we can study the states of this magnetic states of iron-based materials. One such magnetic state study is the relaxation spectrum. So if you are having a ferromagnetic or antiferromagnetic material, you will have a spectrum as noted here on the left side bottom. Okay. And when you make the size of the particle to very small, you are reducing the size. When you are reducing the size, what happens? The spectrum will become a double line pattern like this, as shown in the right side top. Okay. Right side top, you have the double line pattern. So that is giving rise to the relaxation spectrum as a result of small size. Okay. And this is known as superparamagnetism. Superparamagnetism is a small size effect where the same material which is showing a 6-line pattern, when you reduce the size, it becomes a double line pattern, doublet pattern. Okay, that's a result of small superparamagnetism. Okay, and that has been studied by us. So if you are seeing 20 nanometer manganese zinc ferrite, you are having a double line pattern, and when you are having a 25 nanometer particle at 16 Kelvin, very low temperature, you will be having a 6-line pattern. 6-line pattern like this. So you are having this difference in the line spectrum due to the size effect. Why? Because no, it is showing a relaxation effect. Relaxation is like no, your magnetic spins are rotating very fast when your size is small. Why? Because now your thermal energy becomes dominant. V is the volume, K is the anisotropy. So when your volume reduces, your thermal energy will dominate. When the thermal energy dominates, what happens? Your magnetic moments will fluctuate. So the effect of thermal energy is to fluctuate the magnetic spins. As a result, no, you will have a double line pattern. But when your spins are stable, then what will happen? You will have a 6-line pattern. So in the case of magnesium ferrite, we have established the superparamagnetic size, critical size from the Mossbauer spectrometry. Okay. So then another important application of magnetic nanoparticles is like in the case of oil water contamination. Your oil can be separated by surface modifying magnetic nanoparticles, and you can separate it using a magnet. So you can separate very easily oil. You need not one by one. No, we cannot use. We need not use filtration. Okay, we can easily separate it. So for this, magnetic nanoparticles are used, and these magnetic nanoparticles can be characterized using Mossbauer spectrometry as well as vibrating sample magnetometer. Okay. So we have used magnetic nanoparticles for also drug delivery. Drug delivery, in case of drug delivery, people already know, you may be aware of drug delivery technique where you can coat the magnetic nanoparticle with the drug and we can target it to a selected region using an external magnet. So that has been also studied by us. Okay. So another one area where we have undertaken the study is the case of magnetic nanoparticle hyperthermia. Okay. So that is now you inject the magnetic nanoparticles onto cancer region, and you apply an alternating magnetic field. So that will produce heat, and that heat can be used to destroy tumor. So there also you can use the magnetic nanoparticle. Why I am telling all these applications? Because in all the applications we can use superparamagnetic nanoparticle, and superparamagnetic nanoparticle is used here, and we can characterize it using Mossbauer spectrometry. How can you determine whether it is superparamagnetic or not? If you are having a doublet, it is superparamagnetic. If it is sextet, it is ferromagnetic. We need superparamagnetic nanoparticles for most of the applications which I am listing here. Okay. One such application is the hyperthermia, magnetic nanoparticle hyperthermia. Okay, I am not going into the details of this hyperthermia. I am just highlighting here the small particles, 10 to 12 nanometer sized iron oxide nanoparticles can generate more heat. You see here. Okay, it can generate heat up to 16 to 20 degrees centigrade within a time duration of 200 to 250 seconds. But if you are having a large particle, magnetic nanoparticle, it cannot generate heat. Okay, your temperature will not increase. So depending on the size only, no, it can generate heat. When it generates heat, you can use it to destroy the tumor. So this experiment done in our lab demonstrated that now if you have Fe3O4 nanoparticles, this is placed at the center of the coil, and with the time you see that no, there is heating induced on the magnetic nanoparticle, so which demonstrate that no, you can use it for hyperthermia, that is cancer therapy. Okay. So this figure also tells you that no, you can have large heating with the magnetite. Okay. If you are having a high anisotropic material such as cobalt ferrite, then the heating will be reduced. Okay. So what is the basic idea behind the heating? The basic idea is Neal and Brownian relaxation. Neal relaxation means the rotation of the magnetic moments. Brown relaxation means rotation of the particle by itself. A whole particle can rotate, then that is brown. If the magnetic spins are rotating, then it is Neil. So these two relaxations are only giving rise to heating. It depends on the anisotropy constant, K value of the material, type of magnetic material, and the size of the material. Okay, that will give rise to optimum heating. Okay, that is how we have. So now we have established that magnetite nanoparticles can be produced in our laboratory, and it can be straight away. It can be used for magnetic nanoparticle hyperthermia applications. That is cancer treatment applications. Other areas that is emerging areas are like magnetic particle imaging. So we already know about MRI. We already know about CT scan. So this magnetic particle imaging is a very, very cheap technique compared to the other imaging techniques. This is also harmless. So if you see CT scan, no, it has X-rays. So, and also if you see MRI also now people used to inject some contrast agents, such as gadolinium-based contrast agents. So that is sometimes harmful for liver patients and kidney patients, kidney failure patients. So in order to avoid this, we can use magnetic nanoparticle imaging, which can be used to map our body regions. Okay, whether it is your body liver is enlarged or not, or whether your liver is damaged or not. So those things we can study using magnetic nanoparticle imaging. This was developed only in the year 2005, and in the future you may see this in the day-to-day life. So recently there was a report, in 2021, a Chinese group has reported that we can also detect COVID using magnetic nanoparticles, which is very, very fast sensing technique. In the sense you attach the coronavirus to this magnetic nanoparticle. Okay, so the coronavirus, when it gets attached, then what happens? The Brownian relaxation will be altered. I told you that the heat generated by the magnetic nanoparticle depends on the Brownian and Neal relaxation. So there you came across Brownian relaxation. Okay, Brownian relaxation is the rotation of the particle. So when you are having a free particle and a particle which is attached to someone, then the rotation will be, the time of rotation will be altered. That is the basic concept behind detection of coronavirus. So you see that the Brownian relaxation time is altered with the concentration of the mimicking coronavirus. So that can be used to determine the determine the concentration of the coronavirus. That is how far you are infected. So we are developing this technique, that is magnetic particle spectroscopy, in our laboratory for measurement of Brownian relaxation. So this has tremendous applications. Okay. So then, so far we have learned about these applications with the use of Fe3O4. That is magnetite. Okay. So, but for applications we need a strongly magnetic material. But magnetite, the magnetization is nearly only 90, approximately 90 EMU per gram. So if you want to use magnetic nanoparticle for any of the applications, then we should have a large magnetic moment or large saturation magnetization. So the candidates are iron and iron cobalt. But the problem, why people are not using iron and iron cobalt, as you know, the iron and iron cobalt, they can easily oxidize and it can turn to iron oxide. So you prepare iron and iron cobalt nanoparticles, and by the time you reuse it, it will oxidize. Okay. So there is a problem of stability. Also there is a problem now, how will you prepare it? It is oxidizing. If you are preparing using chemical method, then by the moment you prepare it, you will be getting only iron oxide. So this is the future. We need strongly magnetic nanoparticles, but stable. Okay. So the candidates are iron and iron cobalt. I will just concentrate on the technique available to prepare metals and alloys. Polyol process. Polyol process can be used to prepare metals and alloys. You can see gold-based materials which can be prepared here, and you see here gold will turn its color from yellow to blue as the size reduces. This is one of the property of nanoparticles. So you can prepare gold very well using polyol process. So if you are having a high standard reduction potential, positive standard reduction potential, that implies you can prepare that using polyol process. And if you see iron, this is having a low standard reduction potential, but still we have prepared iron. So in this you see that this becomes the limit now, because so far the availability only up to iron is there in the case of polyol process. So when you prepare iron, we can prepare other iron-based alloys also using polyol process. So we tried to prepare iron cobalt and successfully prepared iron cobalt for the first time. And you see here, this is the X-ray diffraction pattern. XRD can be used to find the crystal structure. For iron, this is body-centered cubic crystal structure from X-ray diffraction. You can see 110, 200, 211 peaks. And for the iron cobalt also, you can see that there are no impurity phases. You are not seeing any iron oxide. Iron oxide will come around here. The peak can be easily found. Okay. So from this, we have seen that we can prepare pure iron cobalt using polyol process. And we characterized it using Mossbauer spectroscopy. And the iron cobalt was also it is flower-like in shape, with an average size of around 150 nanometer. And when we characterized using Mossbauer spectroscopy, it was confirmed that it was iron cobalt from the hyperfine field. Okay. So 6-line pattern. So it is ferromagnetic hyperfine field, and it was showing a value greater than 350 kilooyster or 35 Tesla, and it was also shown that we also have a superparamagnetic fraction from the double-line pattern. It was also shown that the iron cobalt was disordered, meaning if you are having a cubic crystal structure of iron cobalt, then the corners are occupied by, if it is occupied by iron, and if the body-centered position is occupied with the cobalt, then it is ordered. Okay. So corner positions are iron and the body-centered position is cobalt, then I can say it is ordered. But if the iron and cobalt are randomly occupied, okay, anywhere it can occupy, then it is disordered. So from a Mossbauer spectroscopy, and if the hyperfine field is greater than 35 Tesla, we can say that it is disordered. So we have shown that iron cobalt is disordered, prepared through polyol process. So this has been published. And recently we have also shown that when you reduce the size of iron cobalt, remember the previous thing, case you can see that it is 150 nanometer. Here it is much smaller. So you can see that in the case of nanomaterials, that is when you have iron cobalt, you also have a oxide shell which is made up of gamma Fe2O3. This is ferrimagnetic. And when you are taking it to room temperature, this becomes superparamagnetic. So from the fraction, that is double at room temperature, it is super paramagnetic, and when you go to 77 Kelvin, the doublet gets disappeared. So that means no, it is more stable at low temperature. Okay, low stable means no magnetically. Okay, magnetically that is no, it is not fluctuating. So you are at 77 Kelvin, your double line pattern becomes 6-line pattern. So that means no, you are having an iron cobalt core and a super paramagnetic oxide shell. What is the advantage? Thing is no, you are having highly magnetic nanoparticle. At the same time, you are having a biocompatible iron oxide shell. This can be used for biomedical application. So in the future, we may be having highly magnetic core shell nanoparticles which are biocompatible, which can be used in lot of biomedical applications, which I have told you previously. Biomedical applications such as no hyperthermia, magnetic nanoparticle hyperthermia, magnetic nanoparticle imaging, MRI contrast. So lot of applications can emerge in the future. Okay, because now people are now moving towards core shell nanoparticles that are highly magnetic. So Mossbauer spectrometry can be used to characterize the phases. They can be used to characterize the magnetic state, that is no ferromagnetic or super paramagnetic. So the magnetic state can be easily found. So those are some of the applications. So in summary, I can say that no, the local magnetic behavior of Fe based compounds can be identified using Mossbauer spectroscopy. Then in the future, for future prospects, I can say that no, highly magnetic core shell super paramagnetic nanoparticles, they are the future. They can be used in lot of applications. Okay. So I would like to acknowledge Professor Greenwich for Mossbauer measurements, Professor Narayanasamy for introducing me to Mossbauer spectrometry, Professor Jaydevan, while I was in Japan, he used to help me in synthesizing nanoparticles, and my PhD students, Prakash, Arun, and recently Rajesh also has graduated. So now we are having Jacob and Shiba who are working with the magnetic nanoparticle hyperthermia. I also thank DST for the funding. So those who are interested in any PG projects, they can contact me. These are some of the project areas that includes biomedical applications of nanoparticles. Then also I have an interest in astronomy, where we used to do theoretical project due to the pandemic situation. So thank you very much.
Thank you, sir, for fulfilling us with your advanced information and making the session worth for attending. It's time for Q&A session. The participants can ask questions or post their questions in the chat box. I once again repeat, the participants can ask questions or post their questions in the chat box.
Any questions?
If you don't feel shy, probably you can post it in the chat box, or probably you can contact me via other social media platforms. That's also fine. Okay, so there was one question. What is the fate of magnetic particles in the drug? So magnetic particles can be targeted, and after that it can be removed using an external magnetic field. So after treatment, we can remove it using external magnet. So it can be removed, or even if some particles are left over, it is biocompatible. It will be cleared by the liver and kidney. Will they accumulate in the body? That is why I told you, like it can be cleared by the liver and the kidney.
So there is another question.
Yes.
Will they accumulate in the body?
It will accumulate, but in a very small quantity. But slowly it will be eliminated. After accumulating it will accumulate only in the liver and kidney. That's what I told you. And as like any other drug, so it will be cleared. In fact, no, your body itself has magnetite. So if you see the hemoglobin system, so it has iron in it, and if you see our body has ferritin. Ferritin has iron reservoir. We need iron. Our body needs iron for the basic functions, basic physiological functions. So we need it. So if there is a deficiency, then we say that it is anemia. So when a person is anemic, especially at the old age, then they used to inject iron injection. So iron oxide, iron-based system, they are not harmful compared to other drugs. That's what I say. So even if it is accumulated, it is accumulated in the liver and kidney, so that will be removed in the due course. Okay.
Shall we wind up the session?
Yes.
Good morning, friends. I feel honored to express my sincere thanks to our resource person of this session, Dr. R. Justin Josephus, Associate Professor, Department of Physics, NIT Trichy. Sir, we have acquired basic knowledge on Mossbauer spectroscopy from your presentation. You have introduced us the mind-blowing application of Mossbauer spectroscopy, like detection of water traces in mass, cancer therapy, water treatment, etc. So your lecture is simple and lucid for everyone to understand, and this session is useful for our research scholars and students to pursue their advanced research. On behalf of the management, Department of Physics, participants from inside and outside the college, I extend my heartfelt thanks for you. Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you everyone. The participants are requested to fill the feedback form through the link provided in the chat box. Dear participants, the next session will start sharply at 1:25 p.m. Kindly join us on time.
There are few announcements for the participants. Please wait.
Dear participants, the paper presentation session starts sharply at 1:30 p.m. The paper presentation is split into two teams. All the UG, research scholars, and Team A members are requested to join the Team A link given in the WhatsApp group. Third UG, second PG, and Team B members given in the WhatsApp group. The duration of the paper presentation is restricted to 3 to 5 minutes. Thank you. Put it.